In this module and the next 4 to 5 modules, we will be talking about a solution method which is called as the integral method. We saw similarity method earlier and we realized that similarity method was mathematically quite exhaustive, involved, and at the end of doing the analysis of similarity method, you would get a partial differential equation transformed to an ordinary differential equation in the new independent variable eta, and therefore, you would have to go to differential equation solver or solution algorithm to get the solution for the dependent quantities, that is u, v, etc. If you also notice, similarity method was, you had quite a few restrictive assumptions in that it would not be valid for any conditions, only specific cases where the similarity variable would satisfy the required conditions would be acceptable. Integral method on the other hand is a very user friendly method. The good part about integral method is that you can do the analysis using paper and pen. You might never need to go to a computer to get the solution. Of course, complex profiles you would probably need to do so. The idea of integral method is that the equations are exact, the solution method is approximate. The basic principle of integral method is that you would assume, suppose you are solving for the momentum equation, you are solving for the velocity distribution, and what you need physically important quantities would be your momentum thickness, displacement thickness, so on and so forth. So, as an engineer, we are interested in coefficient of friction if you are talking about flow, Nusselt number or heat transfer coefficient if you are talking for heat transfer. These quantities are what are the final objectives that one looks for in the solution of the Navier-Stokes equation and the energy equation. What you get in between is u, t temperature, u, v, w the velocities. These are then transformed to coefficient of friction tau wall divided by 1/2 rho u infinity squared, or Nusselt number is minus k dt by dy at y equal to 0 divided by some reference temperature times the characteristic dimension, so on and so forth. So, the idea of this integral method is whatever is the dependent variable you are trying to solve for, be it u, be it temperature, you assume a profile for the same. So, you assume a velocity distribution or the temperature distribution, substitute that profile in the integrated momentum or the integrated energy equation. I will talk about momentum equation, the same logic is valid for the energy equation. So, substitute the assumed profile. So, the profile could be a polynomial, trigonometric, logarithmic, any profile, but you cannot just take any function and expect it to satisfy the boundary conditions. So, there is always a catch, there is no free lunch. So, you choose a profile such that the boundary conditions are satisfied, there is no compromise on that. So, if it is a polynomial profile, a plus b eta plus c eta squared, where eta is equal to y over delta, delta is the boundary layer thickness which is increasing with x. So, the u by u infinity, which is the local velocity divided by the free stream velocity, u by u infinity. Let me just write this down instead of talking. If I assume a profile u by u infinity is equal to a plus b eta plus c eta squared, where eta is equal to y over delta x. This eta has nothing to do with the similarity variable, this is different, this is just a term which is, or a nomenclature which is used for this ratio y over delta x. Okay. So, if this is my boundary layer, flat plate, boundary layer delta as a function of x, this is a y, this is y 1, this is another y 2, this is y 1 here, y 2 here, y over delta x in each of these cases is going to be different, because this is the flow direction and the boundary layer thickness is increasing along the flow direction. This is your x and this is your y. Same diagram follows us throughout the course. Now, how do I get A, B and C? This A, B and C would be obtained from boundary conditions. These could be constants or expressions, whatever, but the fact that each problem is different, you can assume the same polynomial profile, but A, B, C, D, so on and so forth. You can have higher order polynomial. The problem is you would need additional bound. How many boundary conditions one would need for this? You would need 3 boundary conditions to get A, B and C. And off the top of the head we can say at y equal to 0, u equal to 0, that is the boundary condition number 1. So, that means eta equal to 0, u by u infinity is 0. Second one, at y equal to delta, u equal to u infinity, that means eta equal to 1, u by u infinity equal to 1. This is the second boundary condition. Okay, like this I have to develop additional boundary condition, so that if I substitute 1, I would get u by u infinity equal to 0 equal to a plus b times 0 plus c times 0 square. This is B C 1. This gives me a equal to 0. Similarly, if I put the second boundary condition, I would get B C number 2, u by u infinity is 1, a has already been taken as 0, I would get b into 1 plus c into 1, implies b plus c equal to 1. I have to have a third condition which gives me another relationship between b and c, so that I can solve for b and c separately, and therefore, I would get u by u infinity is a function of a plus b eta plus c eta square. Additional greater the accuracy of the solution means you need a higher order polynomial, but for that you need to have additional physically relevant boundary condition. I cannot have any random boundary condition needs to be physical. Okay. So, the basic methodology is that you assume a profile, substitute for the profile in the integrated momentum equation, we will derive this today, integrated momentum equation. In this you substitute for u by u infinity. You do not directly use u by u infinity. There are integrated quantities like displacement thickness, we are going to define that, momentum thickness, which will be appearing in the integrated momentum equation. So, you would have an ordinary differential equation in terms of boundary layer thickness, displacement thickness and momentum thickness. All these would be directly functions of u by u infinity. So, you would have expressions for each of these would in turn be used in the integrated momentum equation. So, indirectly you are getting this or this or this which are directly related to the u by u infinity or the profile that you have chosen. What is the advantage of this integral method? I can have a very realistic problem for which this solution methodology can work. Yes, the complexity may be very high, but the methodology will work, and you might have to do a lot of algebra, a lot of maths to get the appropriate coefficients. Some of them would be expressions which run into a page or two. So, but the bottom line is you will always be able to get the expression for the correlation, it may be for the coefficient, but it may be mathematically intensive depending on the complexity of the problem. Once that is obtained, it is a matter of solving the integrated momentum equation to get the delta star or theta or whatever is needed. So, there are no assumptions which are made in the derivation other than the boundary layer assumptions. Okay. The method is good, the solution is approximate because of the fact that you are fitting a profile, fitting a curve, and unlike similarity method where the solution was there for every x and y or every eta. Here you are going to satisfy quantities at an integral level. That is the biggest difference between similarity method and integral method. Your equations are exact, but solved in an approximate manner. Closed form solutions are possible definitely. You can have arbitrary variations in the free stream velocity. It can increase, decrease, whatever. I can have a case of suction or blowing where V is not equal to 0 at the wall. So, V wall not equal to 0. I can have any kind of condition for which this methodology will work. It may be mathematically very intensive. That is the only catch. Okay. Before we get started with this method, we will have couple of definitions from fluid mechanics that we will have to revisit. One is displacement thickness, other is momentum thickness. What is displacement thickness and momentum thickness? So, if you take a boundary layer, this is the boundary layer, this is delta as a function of x. What we are trying to say is the streamline at the edge of the boundary layer in the free stream. This is highly exaggerated, and the boundary layer thickness is not so big. It is highly exaggerated for our convenience. This displacement thickness refers to distance from the plate where the outer streamline is going to get displaced because of the presence of the boundary layer. If there were no boundary layer, all the streamline would be parallel to the plate, but because there is a boundary layer which is like whose thickness is increasing along the flow direction, the streamline here is deflected by a small amount, and that deflection from the wall which is there because of the boundary layer is called as displacement thickness. If there were no boundary layer, the streamline would just go this way. So, what it is telling is this displacement thickness is given by symbol delta star, displacement thickness this is given by symbol delta star. So, if I take this boundary layer and apply conservation of mass to this control volume, u infinity is the velocity here, this is the velocity profile. This deficit in the mass, this is the, if the velocity was u infinity, this would be the mass that is going in, mass that is coming out at a given cross section. But because there is a deficit in the velocity given by the shaded region, you would have to account for that by the so called displacement thickness, which would have the additional effect to capture the same mass flow rate. Okay. So, distance that is streamlined just outside the boundary layer is deflected away from the wall due to the presence of the boundary layer. So, if I apply conservation of mass over a control volume, which is basically this, I would say this is integral 0 to infinity rho into b is the width into the paper u infinity dy minus 0 to infinity rho u of y into b dy. This is the incoming mass, this is what is going out at a location x, this is at inlet at x location. So, this is the incoming mass, outgoing mass that is equal to 0, mass has to be conserved. So, we are just using rho v dot n cap dA equal to 0 over the control surface, same thing only. We are now writing it as mass in negative, mass out positive, right hand side is 0. So, I am just writing it in a convenient form where this is looking at positive, this is negative, and the additional thing that is going out is going to get captured with the negative sign here, because this is the part which is going out in the inside the boundary layer. The additional part would have a negative sign because this was a part of the outlet term. When I take it to the right hand side, it would become positive. That is basically given by B delta star u infinity, rho into area into u infinity, because the velocity at a location beyond delta of x is nothing but u infinity. So, when I cancel for incompressible flow, rho gets cancelled, B also gets cancelled in this expression. I am left with delta star is equal to u infinity minus u dy. Here there is a u infinity which is 0 to infinity. Therefore, delta star by definition is integral 0 to infinity 1 minus u by u infinity dy. This is my expression for the displacement thickness. This I will split up typically. So, when I assume a profile, u by u infinity will be substituted here. I evaluate this integral. Now, you will ask me what is this u, what is this 0 to infinity? How far is infinity that I need to take? Well, life is very simple, because the definition of the boundary layer, this integral can be split from 0 to delta, which is a function of x, plus delta to infinity, correct. Now, between delta and infinity, u is equal to u infinity, therefore, integral is equal to 0. So, this identically becomes 0, because the velocity here beyond delta is u infinity, is nothing but the free stream velocity. So, 1 minus u by u infinity goes to 0. So, therefore, though delta star is defined from 0 to infinity, in effect I am actually dealing it from 0 to delta 1 minus u by u infinity dy. This is what will be used. So, what we are going to get, boundary layer thickness comes into the equation for delta star. You substitute here 1 minus u by u infinity, you will integrate it with respect to y. The limit has delta, which is a function of x. The delta therefore would go into the right hand side. Ultimately, I would get delta star is a function of delta x. What is delta x? Local boundary layer thickness. This is displacement thickness. Now, this displacement thickness can also be defined or can also be looked at as an imaginary increase in the thickness of the wall, so as to accommodate the presence of the boundary layer. So, if you are looking at as an observer from outside, it is as if the wall has become thicker by this amount delta star to account for the presence of the boundary layer. The second definition which is useful is momentum thickness. We also have enthalpy thickness, which we will define later. Momentum thickness is given by a symbol delta 2 or theta. Fluid mechanics people use theta, because they do not have to worry about temperature. However, in heat transfer, we have theta typically representing temperature local minus T infinity or non-dimensional temperature. We have any of these, and therefore, we will stick to delta 2. Occasionally, we might use theta, but please take it in context. So, delta 2 or theta is the momentum thickness. What is it? It is exactly the same concept as what was used for displacement thickness. The fluid, when it comes in before it enters the boundary layer, comes in with a velocity u infinity. It brings in momentum, which is equal to rho u infinity into A, mass flow rate, times u infinity. So, it is in effect per unit area, if I say, it is nothing but rho u infinity squared, right. When the fluid exits a control volume, which part of which is in the boundary layer, the mass that is being carried out at that location is obviously smaller or lower than what came in because of this velocity profile. So, the momentum that the fluid is carrying out, if I look at a control volume, which let us say is given by this one, the green one is my control volume, right. So, this control volume is having a velocity at exit. Remember, the velocity profile would always be such that it is 0 at the wall and 0.99 times u infinity at the edge of the boundary, that is the definition. So, I have a region which is deficient in velocity, and the streamline which is displaced is just going to be this. This is my displaced streamline, and it is as if I am talking of this additional mass which is required to carry away this momentum, such that this momentum inside the unshaded part and the purple shaded is equal to the momentum that is brought in. Okay. So, we will go through this step by step. So, if I apply Reynolds transport theorem, if I apply Reynolds transport theorem to the control volume shown here, we get this, we would get the same thing for displacement thickness. So, for momentum thickness, what do we need to do? For theta or delta 2, I would write sigma f x is equal to minus f of drag. If I take this as the drag in the x direction, f of drag in the x direction is equal to integral over the control surface rho u v dot n cap dA. This is x direction. So, this is u, this was the mass flow rate, and this is the rate of change of momentum. We are assuming steady state, we are assuming incompressible, and all the assumptions that go with the analysis of a boundary layer. So, what are we having? Minus f drag is equal to integration over the control surface is necessarily going to be mass flow rate times the velocity. What is the velocity here? Mass flow rate in the inlet, that is rho u infinity. B is the width into the paper, B is the width into the paper, y is the dy is the thickness of this strip that I take. So, if I am going to integrate this, I am going to write this as rho b 0 to y, capital Y, this is capital Y, not the variable, capital Y plus delta star local u square dy. How do I get this? All of you would know this. This is nothing but rho b u into u dy integrated from 0 to y plus delta star. What is this capital Y? Capital Y is the edge of the boundary, this one, this green control, the green dash line is at a location, is at a distance capital Y from the flat plate. So, that is y plus delta star, because the at the exit the displacement thickness of delta star is the amount by which the streamlines have been displaced or have been moved. So, this minus inlet or incoming is rho b u infinity squared dy evaluated between 0 to capital Y. Why capital Y? Because at the inlet the thickness is only capital Y. So, if I simplify this, so minus f drag is equal to rho b 0 to capital Y u square dy plus rho b capital Y to delta star. I have just split this into 2. This one is being split into this u squared dy minus rho b 0 to capital Y u infinity squared dy as it is. Okay. So, this I can write, I will change the sign. So, f of x is nothing but, so this is going to be positive rho b u integral 0 to capital Y u infinity square dy minus rho b 0 to y small u local u square dy minus 0 to b capital Y to delta star u squared dy. Now, let us look at this term. This one, what is the velocity beyond the edge up to delta star? Here u equal to u infinity, correct? U is equal to u infinity. So, this integral therefore becomes f of x is equal to rho b 0 to y u infinity square dy minus rho b 0 to capital Y u square dy minus rho b u infinity squared comes out because it is a constant times delta star, this one. Integral dy is nothing but sorry there was a small here, this should be y plus delta star y plus delta star. Integral dy would be y evaluated between these two limits, y will cancel off and it is just going to be delta star. What are we doing now? Just a little bit of maths. So, I now substitute for the displacement thickness inside here. So, I write this as rho b 0 to capital Y u infinity square dy minus 0 to capital Y u square dy minus u infinity as it is 0 to capital Y u infinity minus u dy. This is my definition of displacement thickness, or we had it in the previous slide, u infinity delta star is equal to integral 0 to y u infinity minus u dy. This was there. So, I substituted this for the displacement thickness. When I do that and open the brackets, some things will cancel off and I am going to be left with f of x is equal to rho b integral 0 to y u times u infinity minus u dy. Okay. Now, this momentum thickness is basically what is going to take care of this momentum deficit which has happened. So, I will write the momentum thickness times the mass flow rate. So, it is going to be theta into b rho u infinity squared. This is the momentum deficit due to velocity profile. This theta is that thickness which we are going to define. Therefore, rho b u infinity square theta, instead of that I will use delta 2, this is delta 2, that is equal to rho b u infinity minus u dy 0 to capital Y. If I separate everything, I would get 0 to infinity, because y can be taken as infinity 1 minus u by u infinity dy. This is my definition of the momentum thickness, and this can be written exactly like your displacement thickness, splitting it between 0 to delta and delta to infinity. So, in effect we will be using this between 0 to delta 1 minus u by u infinity dy. Okay. So, this deficit is what is going to take care of the loss of momentum because of this velocity profile. We define that quantity in terms of the inlet mass flow rate and the inlet velocity, that is u infinity, and just it is like a fudge factor. So, theta into rho b u infinity squared. So, in the next module we will derive the integral momentum equation and then solve for the velocity distribution. Thank you.